We were working last time in section 14.4. Do you remember the topic we were working on in general? Surface area, that's right. So we were talking about the area of all these different surfaces that are three-dimensional. We've talked about the surfaces themselves quite some time back, but we're actually looking at finding the area on their surfaces now. So here is a shape, a right rectangular prism. Don't ask you to look in your book. That's like cheating. See if you can come up with what you think the area formula, the surface area formula would be for this shape. So like we can get the area of one side of it. You know how to find the area of a square, of a rectangle. Those are the shapes that we've got here, rectangles specifically. So see what we would have to do to find the surface area of all of the surfaces combined. What did we come up with?
2 times, or h times w times 2 plus length times width times 4.
I think that's close, but not quite. Did anybody get something slightly different?
If the first one is right, but then the second one, would it be 2 length times width, and then it would be 2 height times length?
There we go. Okay, so we've got three distinctly different sides of our box. So one side, this is the one that Elena mentioned first, is the height and the width, this piece right here. So this one's area is HW. And this one right here mirrors the image of this one over here. So there's 2 of those. And you'll usually see the 2 written in front, but it doesn't really matter. On the bottom, you've got this length and you've got this width. So that's the bottom of the box, which is identical to the top of the box. So that's 2 length and width. The other one right here is the front of the box. The front of the box has a length of L, but it has the height W of it. So you have L and H, excuse me, and then you've got the back of the box that's the same image. Okay? So we have double each of the faces because there's really just 3 distinctly different faces of this box. So usually, I'll rewrite this sort of the way you'll see your book have it written. It'll write the 2 at the beginning. And the order of these doesn't matter, right? When we did height and width first, but it doesn't make any difference because we have commutative operations. All right, let's take a look at a few others. So that one's one that's pretty accessible. You guys can work with it. You can see the details kind of from your own creation. This one, the next one's a little bit more difficult to see, so I'm going to go through it with you. So imagine you have a right circular cylinder. So the easiest image that I think to make sense of this with is imagine that you have a soup can. Okay, and the reason I like the soup can is because we take tops off of soup cans all the time, right? You use the can opener, you open the can. You can take the label off of a soup can. So basically we're trying to find out the area on the top, you know, the can, the bottom of the can, and then the area around the label of the can. And that's what this is doing. So they're sort of cutting along the side of the can, kind of like you would cut along the side of a soup label. Okay? So what do we have? Well, you've got the area of the top and the bottom. So these are just circles, and the area of a circle is pi r squared. That's simple enough. And you've got 2 of them because you've got a top and a bottom. So that's where the 2 pi r squared comes from. Pi r squared and then 2 of them. The other piece right there, though, is going to be a rectangle shape, right? Imagine you unrolled this soup can label and flattened it out. It's a rectangle, right? The rectangle has the height that's the same as the height of the soup can, so that's the H that you're getting right here. And then its width of the rectangle is the circumference of the circle. It's exactly what went around the can. And the circumference formula of a circle is 2 pi r. So you take the 2 pi r circumference, which is now the length of your rectangle times the height of the soup can, and you have that's called lateral, the lateral area of your soup can. Does that make sense? Okay. We're going to do an example of one now, and I think it actually is a soup can, some kind of can. Yeah, a soup can. Soup can has diameter 2 5/8 inches, height 4 inches. What is the area of the paper needed for the can's label if the label is to cover the entire lateral surface area? Okay, so the image you probably have is the right one in your mind. It's just the paper part, okay? Just the surface area around it. That's also what the phrase lateral means. Lateral means excluding the bases, not the top, not the bottom, just the surrounding, sides areas. So we're looking around the soup can. So in this formula over here, the part of the formula we're actually looking to do is this part of the formula, not the other part. The other part gave me the top and the bottom of the can. I just want the lateral area around the can. So what I'm looking to find is I'll call it LA for lateral area, and it's 2 pi r h, right? Do I know the r? I could figure it out, or I could recognize that these two together combine to give me the diameter, and you could just use it straight from there if you'd like. Either way, you're going to have the pi in there. You're going to have 2 5/8. Let's actually figure out what that is in terms of a decimal. I think it might work a little bit cleaner for us since we're multiplying these things out in a minute. What's the decimal for 2 5/8? 625, thank you. And then my height is 4, right? It's all in inches, so I don't need to worry about, converting, inches into something different or something like that. It's all the measurements match. So what do I get if I take 2.625 times 4? 10.5. So this is 10.5 pi. If you have it in fractional form, it would be 21 over 2 pi. And then if you get an approximation, which makes a lot of sense because we're actually working with a physical object, this would end up being 32.99 pi. And usually 32.99. And then we need units on any of these answers, whichever one we give. What are the units on what I've just found? Inches squared. So we're going to do the square inch notation, IN squared, on whichever version of it we're using. And again, we'll talk, very specifically on the test on which version of it to leave your answer in. Okay, you ready to look at a pyramid? Oh, I'm sorry. Yes.
So the pi, why isn't there 2 pi? So
I replaced the 2 and the r combined because 2 times r is the diameter. So instead of finding the radius, which would mean taking the diameter and dividing by 2, but then multiplying by 2 in the formula, I just replaced the 2 and the r together with the diameter.
I'm just wondering why it doesn't, because if in the formula of surface area, you have 2 pi r squared plus 2 pi r times height.
Yeah. This is the top and the bottom of my can. But the label for a soup can doesn't go on the top and bottom. It's just the lateral area. It only goes around the outside shape laterally, not on top and bottom.
I just have a question.
Yeah. So it is something to be aware of, though, right? I mean, like visually, this makes sense to us that the soup can label does that, and that's fine. But the key word that actually tells us which piece of this we want is the word lateral. Lateral actually tells us to go around the object and not to use the bases. Okay? Any other questions before I go to the next one? Okay. Next one's a pyramid. Pyramids are a little tricky. What they've done in this image right here is you've got the three-dimensional version of your pyramid, and then you've got the net for it. Do you guys remember talking about nets before? Okay, so this net, actually, you can see the different images you have. You have 4 triangles, and you have a square, because this happens to be a square pyramid in the middle, right? The base is a square. So those 4 triangles are all the same. And we can find the area of 4 triangles, and we can find the area of the base of the triangle, which is, well, the area of the base of the pyramid, which is the square, and combine those together. So anytime you see this, they're doing this in general. This capital B right here is written as base, and it means the area of the base. So jot that down for you. When they write down capital B, they mean area of the base. The reason they do this is because this formula doesn't have to be for a square. We could have a hexagon as the base, and that would be okay. Okay, so whatever the base is, we find the area of that base. Okay. The other pieces come from other portions of this. So let's actually just find the area of a triangle in terms of this particular picture. So let's do the area of the triangle on the bottom. So this area right here, what is the area of this triangle? 1/2 the base, which they called little b, times the height, which they called L. Right? Okay. So what you see up here is you see that 1/2 BL right here. I didn't get that squared in very well. 1/2 BL. And that's the area of all of my triangles. It's the lateral height, okay? The slant height. They're calling it slant height over here. So do you see this L is the slant height? So it's not really the height of the pyramid, right? It's sort of this height that's along the side of the pyramid, not straight down in the middle of the pyramid. It's important to realize. And then we have, oops, then we have this N. What do you think this N is representing? It's not really defined on this particular screen. Yeah, N is the number of triangles. And you could say a number of triangles, which certainly works. You could also talk about it being the number of the sides of the base. Like the base of this is a square, so there's 4 sides, right? If I had a hexagon, N would be 6. And then I would get 6 triangles, like you mentioned. Okay? So then we're just multiplying that times 4 in this case, because there's 4 triangles. So you just take one area of one triangle, because they're all the same, and you multiply it by the number of triangles you have to get the area of all 4 of them in this case. Now, they also show you that if you take a look at this a little bit more carefully, the base, let me erase this so I can do it this way. The base, B, is this length. And if you multiply that base by N, the number of sides of the triangle, you get all 4 of these added together. I mean, right? That's what you get. That has another name. It's the perimeter. So another way to think about this is that you could say that you're taking the slant height times the perimeter of the base. Just another way of thinking about it. And again, you still have to do the 1/2 in front because it's triangles that we're taking the sides, the areas of sides of. Okay? All right, so we're going to do an example with this. The basic shape of the Transamerica building in San Francisco is a right square pyramid. So it's like the last picture we saw. It has a height of 260 meters, a square base with perimeter 140 meters. The altitude of each triangular face, that means slant height, altitude of each triangular face is 261 meters. Find both the lateral area and the surface area of the Transamerica building. So let's go back to our picture just a moment and talk about lateral area versus, because I think I skipped over that mostly. Lateral area versus the surface area. The surface area includes all surfaces. All surfaces is surface area. Lateral area excludes the bases. So on this picture, the lateral area would be everything except for the square in the middle, or the square at the bottom, depending on your perspective. Does that make sense? Okay, so as we're taking a look at this, it asks us to find the lateral area, which will be included no matter what. So let's find the lateral area first. So the lateral area is a bunch of triangles. How many? 4 triangles. Okay, so in the formula for the area of the triangle had 2 versions. We can use 1/2. I'm going to write down the way your book does. B, L, N. Or we can write down 1/2 L, P. One of these is slightly nicer than the other one because of the way that they set the problem up. Which one would be the nicest of the 2 to use? The second one, because they give us P for the perimeter, right? I mean, could we use the perimeter and find the sides of the sure, we could use that, but there's no need to. We have the information set up to use this piece right here. So we're going to find the lateral area, which is 1/2 L. What's L going to be in this particular problem? 261. Why is it 261 and not 260? We want to make sure we get the slant height, right? The height of the triangle, not the height of the actual building. That's 261 in this case. And what's our perimeter? 140. Okay, let's make sure that we have units that are the same everywhere, because I didn't do that when I started. Are they all in meters? Good. So no conversions necessary. All right, so let's take 1/2 times 261 times 140. And tell me what you get.
18,270
What are my units, Amy?
meters squared.
Fabulous. That's my lateral area. Did everybody get that value when you multiplied? Excellent. Now, what do I need to do differently to find the surface area?
Area of the base and add it to what we just got.
All right, so I take the lateral area, the one I had just got, and I add it to the base. They call it capital B. Now, to do capital B, the base, this was 18,270. How am I going to find the area of the base?
You could take
What am I going to do?
You have to take the perimeter and divide it by 4 because you know it's a square.
It is a square, yeah.
The side lengths.
My perimeter they gave me was 140, right? So my side length would have to be 140 divided by 4. So what does that give me for my side length?
35.
35. So now I have a 35 here and a 35 here. How do I find the area then of that shape?
35 times 35.
Yeah, 35 squared, or 35 times 35. Add it to the 18,000. Go ahead, what would you have?
The area of the base was 1,225. And then the total area is 19,495.
And units?
Meters squared.
Yeah, square meters, just like before. Make sense? Cones. We're not going to talk too much at length about where these formulas are coming from. They can be, you can cut the side of the cone, just like we cut the side of the soup can, and you can roll it out, and it will form an arc, like it'll form a sector where we've got the arc in there, and you can use that information. It's a little bit more complicated to take a look at, so we're not going to go too far into that, but your book will if you'd like to take a look. The surface area for a cone is going to be much like the other pieces. We've got the lateral surface area, that's the surface of the actual cone shape, and then we've got the base. Okay, so imagine the ice cream cone, right? It's just the waffle part is the lateral area. Okay? The flat part where you actually sit the ice cream in is sort of missing from that perspective. If you found that flat part, that would be the area of the base. So the area of the base, well, that's the area of a circle. So that's the pi r squared that we have here, right? And then the surface area's lateral area portion is taking pi times the radius times the slant height. Okay, so the altitude of the actual triangle, right, from this, the actual height of the actual triangle is uninvolved, just like it was with the pyramid, uninvolved in finding surface area. It will be involved in finding volume. We'll need that later. But for surface area, we don't. I think we have an example. Oh, not yet. We have one more formula before we have an example. Okay. The other one is sphere. The surface area of a sphere is 4 times pi r squared. Pi r squared is area, right? When we look at the surface area of it, we get 4 times as much as the area of the actual circle itself. A great circle is a circle on the sphere whose radius is the same as the radius of the sphere. Okay, so a great circle basically cuts the sphere in half. It creates 2 hemispheres. A sphere has infinitely many congruent great circles. Okay, so you can infinitely cut through the sphere and cut it into 2 hemispheres, right? Of course you can. And the example they give you to think of in terms of a globe is if you think about a globe and you think about the lines of longitude, those are the ones that go up and down across the globe. And you can see how that would, mirror image go all the way around. And there's not just 360 of them, right? It's not one for every degree. You can have them for half degrees and things like that. So there really are infinitely many great circles. And that's just using the North Pole and the South Pole as part of the circle itself. They don't have to be used as North Pole and South Pole. Of course, you can use anything. Okay, we're going to do an actual ice cream cone. Find the surface area of this ice cream cone. And it says to assume that we have a right circular cone topped by a hemisphere. Okay, so a few things here. Notice what we don't have. We don't have the area of the base of the cone, right? It's not part of the surface here. It's somehow inside of it. It's the interior portion. So we only have the lateral part of the cone. And we don't have a whole sphere either. How much of a sphere do we have? A half sphere. Okay, so let's actually create what kind of a formula we're going to need based on the portions of the other two formulas that we have been given. So we're going to have the surface area. We only want the lateral area of the cone. So if you flip back, the lateral area of the cone part was pi RL, right? The part that did not include the circle. And then we want the surface of a sphere, but we don't want the whole thing. We want half of it. So just for the sake of being real clear, I want 1/2 of the 4 pi r squared. And yes, I do realize that's 2 pi r squared, and we'll do that in a sec. Okay, but it's 1/2 of the surface area for a sphere. All right, do we have r, the radius of our sphere? Yes, what is it? 4. So this is pi times 4. Do we have L for our cone? We don't, actually. 8's not L, is it?
No, that's the height.
It's actually the height. So how are we going to find L, which should be right here? There is a triangle there. Specifically, what kind of triangle?
The right triangle.
Oh my goodness, it's like we almost combined this with something else we've already done. Heaven forbid. Here's an 8 and here's a 4, and how are we going to find the other side? We're going to use the Pythagorean theorem. You got it. Okay, so Pythagorean theorem says, we'll keep calling this L, that the base side, or the legs of our triangle, which are the 4 and the 8, are individually squared, and they have to equal the hypotenuse squared, which is my L squared here. So if I take 4 squared plus 8 squared, what do I get? I'm sorry, I don't have this one written down for some reason. Is it 80? That sounds right. Yeah, 80. And then we're going to square root that. So eventually we're going to want, we'll keep this exact for now. Let's see. 80 is 4 times 40. 40 is another 4 times 10. So these two 4s. Oh, I'm sorry, times 20. Thank you. I'll fix this, sorry. Moving too quickly. 4 times 20. Thank you. And then I have 4 times 5. Okay, so there's 2 4s here. So when I do the square root of 80, I can bring the 4 out. So this is 4 square root of 5. Plus, I've got my 1/2 and my 4, so this is 2 pi. And then I already did the r. I already looked at it. R was 4, so it's 4 squared. So I have 16 square root of 5 pi plus 32 pi. Does that look okay? I can't combine these because one of them has a square root in them, so I can't like add the 16 and the 32 together. That's not allowed. This is what units? Centimeters squared. Now let's get a decimal approximation for it, okay? So find out what is 16 square root of 5 times pi plus 32 pi approximately. And we'll go with 2 decimals unless for some reason that seems weird based on the answer that we're given or we find. Does anybody have that?
I got 212.93.
Is that what you have, Kaylee? You didn't do yours, okay. Elena? Is that what, that's not what you have? Okay. Well, let's get a couple people having the same value before we call it good anyway. Huh? That one is one you have? Okay. So I have 2 votes for 212.93. Not that this isn't democratic, so it doesn't really matter, but is that what you got too, Lacey? Okay. All right, we've got 3. I think we're okay. So this is 212.93 square centimeters. Any questions on those? All right.